Hello and welcome to episode 38 of the Stanford MLSys seminar series. My name is Dan. Today I'm joined by Fyodor, Piero, and our guest, Pooyan Jamshidi. So as always, remember, subscribe to the channel, give this video a like. If you're watching the recording, leave a comment about your favorite part. Before we get started this week, we have a couple of announcements. So if you've been following our website at mlsys.stanford.edu, you'll notice that we don't have any more speakers scheduled for the rest of August. That's because we're going to be taking a little bit of a summer break starting this week. So this will be our last session until around mid-September. And we're also very excited to announce when we're coming back. We'll be coming back as a full Stanford course. So that's right. If you're a student at Stanford, you can sign up for CS 528. That's the Machine Learning Systems Seminar. If you sign up for that course, you'll get some nice perks, like a chance to interact with our speakers a bit more one-on-one after the talks starting this fall. So we'll be back with those starting in mid-September. Meanwhile, for today, our plan as usual is we'll have around a 30-minute talk followed by a podcast-style discussion where you, the live audience on YouTube, can ask live questions. This week, we're discussing Causal AI for systems with Pooyan Jamshidi. A little bit about Pooyan. He's an assistant professor in computer science and engineering at the University of South Carolina. He's also a visiting researcher at Google Ads AI. And he's very interested in the intersection of machine learning and systems. So as you might expect, a perfect fit for our seminar. And today he's going to be talking about Causal AI. So with that, Pooyan, feel free to take it away.
Thanks, Dan. Thanks a lot to the audience, and thanks for the organizer for invitation. So my name is Pooyan Jamshidi. I'm going to talk about Causal AI for systems. And this is if you don't know. Okay. Before I jump into the details, I want to acknowledge collaborators, postdoc, and students who done the job. I'm the lucky guy who only present the work, right? So AIC lab have several members, as you see, and we work at the intersection of machine learning and systems. We have a special focus on type of system we work, mainly robotics, autonomous systems, serverless, and so on. And today I have a specific plan, a little bit of change, but I'm going to talk mainly about some intuitions, right? Rather than mainly results. Also, I have to mention that since this talk has two aspects, one aspect is the system side. I have several collaborators that I'm working with in the systems, different type of systems. And also for Causal AI, I have collaborators, including Mohammad Ali Javidi, who is a postdoc in my group, and several others for different type of systems. And I guess I'm so sorry, I need to update this again because some of the changes are not applied. Anyway. As I mentioned, we are also active regarding Causal AI in robotics, in adversarial ML, and the work in Google, I'm mainly focusing on causal representation learning, working with Sugato and Garima. I have to also announce that we're lucky that we're funded NSF Medium project in collaboration with Columbia, Bashaki Ray, and Carnegie Mellon, Christian Kostner. And this project is a broader perspective toward Causal AI for systems, mainly from different aspects, developers aspect, user aspect, and the whole infrastructure that facilitates basically performance optimization, performance debugging, performance testing, and visualization from the causal perspective. some detail about my work at the intersection of causal AI and representation learning. I don't go into detail, but mainly the work is about attribution, explainability, and I'm developing an attribution method in order to repair representation that has been learned in deep neural network. But this talk is not about this. The outline of the work, I start by a specific case study after I motivate the work. Some description about the opportunities of causal AI for systems. And also mainly the focus would be on performance of system, because we know that system has many different aspects. This work, most of our work is related with respect to the performance in some sense. Some results, if we get time, and maybe some future directions. So these days, many systems are ML-based systems. So this means that a model, typically neural network, sits somewhere in cloud or on device or somewhere in between. These days is mostly about deploying these models on device. We know that these models are getting more and more accurate, but at the same time, they also become more resource intensive. So they demand more resources. Obviously, we don't want to get fat as a result of bad prediction about the system that predict the amount of calorie in food. But on the other hand, we don't want to lose the usability of the system. We don't want to recharge our phone several times during the day because this neural network is doing a lot of inefficient inference. So the goal is to enable both developers and users to find the right quality trade-off. And by quality here is mainly performance. This means that we develop infrastructure, method, tools, mechanisms in order to enable this quality trade-off, which is very important. And trade-off means that in the multi-objective space, because systems, energy consumption is important, accuracy is important, throughput of the system is important. So typically we deal with the system. When we talk about performance of a system, different metrics and different objectives are involved. Also, today's most popular systems are configurable. From Apache Hadoop, that most of you are familiar, to robotic platforms, and more recently, ML systems, as you know. Let me give you some background, some basic definition of what we need here in order to understand the work. Here is the configuration file of Apache Hadoop. As you see, several different configuration options. Here you see the number of threads. Integer, user can change it to any number. Also, you see here the memory size. Also, you can change it. And the user have the ability to change any of these options. But actually, this number of configuration options that you see here is tiny amount of the whole configuration space. So we are dealing with systems that not only have many configurable options, but also this number of options increase over time. So here, for example, Tianjin showed that just from 2006 to 2014, the number of options for Hadoop has increased from 20 to roughly around 200, meaning that tenfold, 10x increase in only 8 years. So this is massive. This means that the problem of finding the optimal configuration become 10 times more difficult over time. And this is actually true for many different types of systems, from storage, such as MySQL, to web server, to data analytic pipeline, and so on. So these number of configuration options increases over time. Not only the number of options increases, but the number of software configuration options increases, but also there are many options live across the stack. Options that I show you were mainly about the software layer, but we know that we have computer architecture, we have macro architecture, we have a bunch of middleware. For example, if you have an ML system, typically use TensorFlow or PyTorch as a middleware. Those libraries, middleware, also configurable. Hardware is also configurable. For example, embedded hardware, you can tune CPU frequency, GPU frequency, even up to the place that you can control the fan speed. So we can consider all of these as configurable options that obviously affect the performance, which is important to understand the impact of these options toward performance. And also in this software life cycle, I will mention later on, there are tasks that requires understanding about options, and more importantly about the interactions of options. And that's why it makes it difficult to do these tasks such as performance tuning, performance understanding, and debugging. In addition to this, many systems are now composable, meaning that they have several different components that put together with a specific architectural style. It is typically through a DAG, a graph, and there are lots of variability as a result of this complexity. Let me elaborate what I mean. Here you see a specific ML system. This is a multi-model ML system. You see a bunch of here. You see a bunch of sensors that capture data from images to video stream to location data to voice and others. You see here several different system components. These are the components that do the post-processing, analysis, and so on based on the data. So you have multiple streams that typically are getting processed through several different components. And you can think of them as some sort of data transformations of different types. And you see here a bunch of different ML models that serve obviously some of these components. And here you see the deployment environment, which you can consider some of them embedded systems, hardware that is typically have a limited resource, and this limited resource is variable depending on the type of hardware. So for example, you could have hardware as small as this, which you may not be able to even fit a sparse neural network, to this one, which is slightly more complex still. You have lots of limitation in terms of resources. And also you have the option of deploying it in cloud, in any cloud, multi-cloud, single cloud. So typically we have a huge variability space. I mentioned about this configuration space so far, but as you can see, there are lots of variability in terms of the system architecture, the way how you compose the system, and also in terms of deployment environment. Where do you want to deploy the system? Specifically this mapping, right? And already considering this configuration space, it was a huge and large space, but including even the architecture and deployment environment make it more complex. So let me explain why I'm emphasizing on the complexity or difficulty of the problem. And here is very simple, simplistic example. You see one option here, and this is option defined by ifdef in C. Depending on the value that is assigned to these options, for example, this option currently is binary, right? Is either true or false. One line of code gets executed if this is true. Otherwise, several lines of code get executed. And imagine this is only the software part of the stack. And this is only one option, right? So as a result, depending on what value is assigned to this, it impacts the performance metrics such as speed or throughput, as well as the energy consumption. And again, this is two possibilities in terms of performance, depending on the two possible value that you can assign to one configuration options. But the complexity, as I explained, is larger than that. And I will go over a specific case study to elaborate further than this. But before that, let me also explain why we are focusing on performance, specifically with respect to the configuration. The main reason is that here is some real examples, real measurements of performance, both in terms of energy consumption and latency in the multi-objective space, and each dot representing one configuration of the system. Okay. Here you see a bunch of black dots. These configurations, and here you see the corresponding probability distribution of each performance metric. Here you see many configurations have low energy consumption and low latency. So these are typically good configurations. These are normal configurations. But you have many others that you can correspond them to performance fault. Some of the faults are associated to latency. These are typically the ones that have higher latency. This means that result in a lower throughput for the system. You have also a bunch of faults that exhibit large energy consumption. And also you have some faults that have both large energy consumption and large or high latency. So this means that it is important to not only identify these performance issues, identify the root causes that resulted in these performance issues, and also fix them, right? Specific example, this is one issue that you can find it here, and a user picked it up autopilot code on GitHub that a developer wrote it and deployed on NVIDIA TX2. NVIDIA TX2 is like this one. And you know that TX2 has more resources than TX1 in terms of memory, CPU, GPU. But the thing is that after he deployed on TX2, he observed performance drop as a result, which was not obvious for this user. After so many conversations on the issue tracking system, you observe some very interesting things. First of all, users not only want to get the performance issue fixed, but also wants to understand the underlying mechanism involved, right? Why? The key reason is that they don't want to face it and they want to fix it earlier than later on, because it involves a lot of back and forth between developers and users, and as a result gets a lot of time in order to fix this issue. Specifically, these default setting also didn't help, and it took roughly around 1 month to fix this issue. And the fix was really not obvious. So there were some compilation flags that needed to set differently the CPU GPU modes and also the fan mode, which nobody expected that fan speed also is involved in this performance issue. So due to these reasons, and this is one specific example, but we have observed many, and you can also for sure find these issues and many more of these with the same characteristic, right? So now that I explained a little bit about the problem and why it is important, let me elaborate it further through a case study, and then we will continue. I'll focus on a specific, again, compose system. This is yet another compose system data analytics pipeline for basically identifying trending topics in social media. So internet and the system has a crawler that searches through internet to find content out of possible resources out there. It stores the content into Apache Cassandra, and then it fetches the orchestrator of the system fetches these tweets that are stored in Cassandra with some regularity, with some frequency. And then it pushes to content analysis for doing some downstream tasks, which are mainly stored in Apache Solr and fetched by users, mainly doing search and also some require integration with some of their system, backend system that require this integration. So that is a real system that I've been dealing with and helping development, but mainly the optimization. So years ago, let me elaborate on challenges. So the company using this system wanted to increase the users to 100x more. Basically, they saw a demand, but they didn't know whether their system could scale to that number of users. Based on some analysis, model-based analysis, we realized that the crawling speed needs to speed up 10 times. The fetching should be closer to real time, and basically, in order to get the scalability, we needed to. There were some few solutions. Obviously, the easiest solution here is that you can throw some money, buy more resources, and as a result, get better performance. But we thought maybe there might be different solution here as well. So we thought maybe let's try to optimize performance or tune performance with changing the configuration of the system. Maybe we don't have the optimal or near optimal configuration, and we can do much better if we do so. So let's see what are the opportunities. We have Apache Cassandra, we have a Storm, and we have Apache Solar. So these are 3 different engines. All of these are configurable. Typically, they have more than 100 configuration options. And as a result, you know that the number of possible configurations of the system is huge, is 2 over 300. We can do the math based on the assumption that the options in the architecture that I presented here interact. What does it mean? Meaning that the options that you have here might interact with the options that you have here. So as a result, the possible number of, because if there were no interactions, it was much simpler problem. But in practice, there are lots of those interesting interactions that happen at the system level. So the number of possible configuration, even with this assumption that all options here binary, simple as that, let alone if we consider like non-binary, like integer, we have much more. So this would increase. So this is really simplified problem. And you see that the number of possible configuration for this system is more than the number of atoms in the whole universe, which is huge, right? So in order to get the best performance, whether this is the best configuration or that one is not obvious. So it's a very difficult problem. Let's see what we have observed. Again, here we looked at the write latency. So this is Cassandra, and also throughput. This is the default configuration, which is located at the upper percentile with respect to write latency, and also lower percentile with respect to throughput, meaning that the default configuration is bad. As you might have guessed, this is the optimal configuration, which gives you the best throughput and the lowest latency for the write operation, which is very far from the default configuration. And this is the configuration that has been suggested by domain expert having some knowledge about the system. And you can see that even the expert suggestions were nowhere near optimal configuration. And again, to remind you, each of these dots represent one configuration for the whole system, meaning that this guy, you have to set all options to a specific value, and the whole thing becomes one configuration, right? So this is the way how it can work. Or more clearly, if you remember the very first slide that I show you, Apache configuration file, setting all of these options give you one configuration for the system, and varying them result in different configurations. More importantly, the performance behavior of systems would change massively sometimes when we change the environment. And by environment, meaning that, for example, changing the hardware or changing the workload of the system, right? And we know that all of these happens for many systems. We have distribution shift in terms of the behavior of user of the system. As a result, the workload for the system change. Hardware, when we deploy on cloud, we don't even have basically control what node exactly is allocated to this process. So there are lots of variability, as I mentioned, and you see here that the performance behavior here, you see like the single model type of performance behavior, which after we change the environment, and this is again like for Apache Cassandra, by environment, we change the workload, right? You see the second mode of the distribution has appeared, and this is again with respect to read latency, one performance objective and its corresponding distribution. I don't want to go further, but I think you got the idea. You got that this was a difficult problem, like more than number of atoms in the universe, potential configuration that you can configure the system that way, and also the performance behavior change across the environment and so on. So at the end, we were able to basically develop a tool that finds the optimal configuration using Bayesian optimization. I'm not going to explain and go over that. That was an example, but I want to now transition toward causality. Why we would like to use causality in order to do some of these system tasks, specifically performance tasks in the system development lifecycle. There has been a bunch of work in the literature from different communities in systems and software, from computer architecture, database, big data, programming language, operating system, and software engineering, which looked at different issues, different software and system tasks in order to address a very particular issue by using causal inference in some sense. So basically, we were not the first, but let me explain some basic concepts before going into detail of the methodology. And please remind me whenever I need to finish, so I don't go over time. So this is a sounds good, yeah. So here you see a very particular causal graph. I want to clarify a few things in this causal graph, what we see, because this is the basic and fundamental model that we construct based on data, observational data that we get from the system in order to do this downstream task from performance understanding to performance tuning and optimization, and also performance testing. For all of this, we need this structural causal model. So this is the first step, constructing this structural causal model, and the rest, all of these tasks employ the knowledge that is encoded in this causal graph. And that's the difference between our approach and the other approaches that I mentioned here. The key difference is that our methodology is unified in a sense that with one model, you can do all of these tasks. And these tasks, you can think about it as different inference or causal inference on top of this structure causal model. So here you see a bunch of nodes like EMC frequency, interval, cache pressure, right? So these are configuration options across the stack. Some of them are software configuration options. Some of them, for example, EMC frequency is hardware options, where with respect to the memory, you see also other hardware options like CPU frequency, GPU frequency, and you also see here nodes of different color, which correspond to system event, right? And these system events somehow are on the causal path, and the interactions between them, and also interaction between these and options also typically are on the causal path. So these are somehow mechanisms that explain why a performance issue happened, how basically these options affect performance throughout these causal mechanisms, right? And we have some of these functional nodes. And these are the fundamental and the most important piece of knowledge in this type of graphs, right? Also, you see of different colors, these are performance objectives. Like you see energy and throughput, and typically you have multiple of them, because I mentioned this is a multi-objective type of problem. So these functional nodes capture the interactions between options. And that's the most important thing in system performance. Here you see a functional nodes that capture interaction between this system event and this CPU cores. Basically, this is option at the hardware level. You know that for this type of hardware, you can disable or enable any core that you want in order to do your task, right? And you know that it has effect on energy, like and it is captured through here, right, toward energy. And also it affects a bunch of other different metrics. So also you see interactions between two system events. And these interactions, you can characterize it different way. And this is important. You can characterize it by different type of models. So for example, for learning this functional node, we can use neural network. There are also work for learning the causal structure, assuming these functional nodes are neural network. And these are like in theory of causal AI, which I'm not going to talk about it now due to lack of time, but these functional nodes can also be characterized using polynomials as well. To give you a specific example, imagine that here for this function, you can consider, you see that it is this guy is the value for this is determined by the interaction between these two, right? So you can consider like F12 is equal, for example, this is very synthetic example, like 2 EMC frequency plus like 10 cache pressure plus 1.1 EMC and cache. interaction between these two. So you can capture this function node even by polynomial of degree 2 or of any degree. And this is like, there are some theory connecting the type of function, the degree of interaction that they can capture, and so on, and how it affects accuracy of the type of inference you want to do on top of this graph, right? So these are the basic definition that you require, and all of these tasks, for example, for performance debugging, testing and debugging, meaning that we observe a performance issue. For example, we saw that the performance issue of a video case, right? Meaning that we have a system that consumes a lot of energy, and we want to debug it. What exactly is the cause of this high energy consumption? And you already see that, like, if you traverse back, you can find possible paths that lead to different nodes, and these are potential causes of this performance deterioration. And using some mathematical concepts and operation in causal AI, which I'm not going to go into detail, you can trace back and find the reason, also be able to repair this performance issue automatically using this the estimation that you get out of this causal graph. Just a quick mentioning, and I will conclude. So this is, for example, one specific type of task which I mentioned about, like testing and debugging, that finds misconfiguration of the system, right, in the whole life cycle of system development. But let me go into detail to finish up. And this is the overall process. It involves several steps. The key is this building causal graph that I mentioned, and the downstream analysis, typically the counterfactual queries that find a fix for this, and the main concept or phenomena in causal AI that enable us to find these root causes is basically this causal effect estimation based on the structural causal model. And for estimating the causal effect, there are foundation in theories and basically findings in causal AI where you can estimate these entities quite accurately, even sometimes using observational data, meaning that you don't even need interventional data in order to do the task. So
Pooyan, I think this would actually be a great point to start transitioning into some of the podcast style discussion portion of the video today, because I think we actually had some questions in the audience about some of the things that you're talking about right now. Pat Langley had a wonderful number of questions about I'd characterize kind of how you model the complexity of the world and how you kind of turn it into kind of like a causal AI, causal ML system. So maybe we could start by talking about some of those. Before we get on, but before we do that, just as a reminder to the audience, feel free to send in questions in the YouTube live chat, and we'll summarize them and help get them to Pooyan. Especially, yeah. So I think now would be a great time to transition since we have around 15 minutes left. So Pooyan, one of the things that Pat Langley was wondering in the questions is kind of how do you, I think, you did a great job of kind of outlining some of the really complexity in deploying these modern systems. You talked about like, how much configuration there was, and interesting, thoughtful questions like this. Um, I'm wondering, how do you take something like that and turn it into kind of a concrete machine learning style task, like with inputs and outputs? Where How do you start collecting that data? Does it come from controlled experiments? Does it come from kind of observational? You just run one of these systems for a while. How can you give us, shed some light on kind of that effort to go from the complex real world into some concrete problem that we can start digging, using causal AI tools and machine learning to help answer?
That's a fantastic question. Let me elaborate on that. So we have a system. Imagine that this is system under test. This is a data analytic pipeline as an example, right? And we want to build causal graph that capture the basically from software configuration option to hardware configuration middleware cross stack, also basically the performance objective and so on. Here is how you can think about it, right? So you can think that you decide one configuration, okay? So meaning that you have all of these options that you can set depending on the exact configuration space that you have defined for your problem, right? So imagine that you set them. You could use any search algorithm or iterative algorithm in order to determine the next. So this could be very random setting of these options that result in random configuration, or could be like based on some heuristic that uses that is incorporated in a search in order to give you the next configuration in order to measure. So you know that for measuring performance, you need to instrument the system. And this is not easy or straightforward. So you not only need to basically instrument the software, right? So you have a bunch of options that you can set at the software, but also you need to have instrumentation for middleware. For example, typically middleware, they export API where you can change the options and get different configuration like TensorFlow, etc. But also hardware level. Like hardware level is also not straightforward. How you want to disable or enable specific options. Fortunately, we have developed some library to facilitate this instrumentation at different levels of the stack. So you configure the system with a specific configuration. Let's call it C1 here. So you deploy the system under test with C1 on a specific hardware, right? And you collect performance, right? So you measure energy and like throughput, or any metric that is important for this system. And from system to system, the performance objectives are different, right? So if this is a data analytic pipeline, typically we want to increase throughput, right? And obviously get lower energy consumption as a result as well. So once we get the performance data, we can associate this performance that we measure both in terms of energy and throughput. And then there you go, you constructed your data structure. So imagine that you have a data structure that have all option value as a vector, and also after you instrument it and measure the system performance under this specific configuration, for C1, you have one line of data, right? So this is one data point that you collected by changing the configuration. Next, you do C2, and then do the same, okay? And you collect all data, and then based on this data, you use a structured learning algorithms, and there are many different structured learning algorithms, causal structured learning algorithms out there that you can use. CGNN, my former student, Mohammed Ali Javidian, who is now postdoc at Purdue and postdoc in my group part-time, his PhD thesis was about causal structured learning. So there are many different algorithms out there that you can use, and then you have your causal graph, right? An example I showed the other day. Does it make sense? Is it clear?
Yeah, I think that's some really useful context for everyone. One thing that's, I think, kind of interesting about this process, that as you kind of lay it out this way, is that one of the things that's kind of striking for me, at least, is that in my mind, I imagine that a domain expert or something like that would be able to pick up on the space. You'd imagine that a domain expert doesn't have to literally change every single config and then kind of stare at it and see what it does. I wonder, is there any work that you know of, or any work that you've been working on yourself, that can kind of incorporate some of that domain expertise in? Because, we humans, we don't have to treat the system as a black box. If I change a certain config, I can imagine what will happen, or I can try to predict. I wonder, is there anything like that that you know about, and that can kind of incorporate some interactive domain expertise into the learning process?
That was a fantastic question. Whoever asked it, that was a fantastic question. Thanks. One of the issues in the whole methodology, or the whole process, is that based on the data that we collect about the system performance, there is no guarantee that this causal graph is actually the true underlying causal graph, right? Nobody knows what is the true underlying causal graph. Each of us, for example, the developer of the system might have some guess about, like, very a small part of the whole causal graph. Specifically, those developers only know about the software part of the stack, right? Most of them have no idea about how hardware options affect performance, right? The benefit that you can get from this expertise is to, first of all, remove the nonsense interactions or arrows that appeared in the causal graph. So expert can correct it, because this structured learning algorithm is based on the data, and there might be some incorrect, for example, if you don't have enough data, some inaccuracy might happen, right? So the experts can correct this causal graph by removing nonsense or not relevant arrows or causal connection. And each causal connection, that basically means that these two variables are not independent. Or add some new causal basic connection between nodes that hasn't appeared, maybe due to lack of data or something like that. So this is the way how experts can contribute to the whole process.
Pooyan, when you build these models, I'm wondering about the assumptions that you make, and Pat Langley kind of had a question about this as well. Are you assuming that these are kind of deterministic relationships, or are they probabilistic? Perhaps you've worked with both. Could you comment on that?
Yeah, so these basically connections, meaning that so this is a very good question. So this connection, so if two variables are independent, they are disjoint, right? So for example, there's no connection between them. If you can prove, or if you can basically test whether two variables based on the data are independent or not. And we have a bunch of statistical tests to do that, right? Even you can consider them as a unit test in order to, to see whether like this connection that didn't appear, whether it should appear or not based on the data you can do after the fact, after you learn the structure, to do this kind of testing, right? But to answer your question directly, basically you can consider them as a deterministic in a way that based on the data that you collected that involve measurement noise, involve a lot of stuff, we want to learn the underlying causal mechanism. And in a way that, and why I'm mentioning this as a deterministic, I mentioned like each of these function nodes could be a deterministic function, such as polynomial regression models that appear based on the data, right? And how they affect the performance metric. But basically, whatever, and against this causal graph, we want to run queries. These queries essentially are formulated based on some conditional probabilities that we want to estimate, right? One clarification, I hope that this does answer your question. And if not, let me know.
Oh yeah, it kind of captures basically the essence, I think. Thank you.
Sorry, I don't know why the sharing disappeared. I will reshare it again.
Maybe Pooyan, in the meantime.
That was actually me. I think we forgot to tell you that we're gonna stop the sharing when the talk's over.
Oh, you stopped the sharing. Okay, sorry.
Piero, I think you had a question though.
Yeah, well, really a quick one, just for before finishing. I'm curious about, you gave a good example that if those configuration parameters were binary, there would be more configurations than out of in the universe. Although these configuration parameters in some cases may not be binary, it can be like either strings, so categories if you want, or they may be integers or float values, even words, I would say, right? And so I'm curious how to determine the ranges and the domains in which you are working for each of these parameters.
Right, that's a very, very good question. So let me basically summarize. We have options of binary, right? Enable or disable. We have option, as you mentioned, like string. Typically, this is like, you can consider it as categorical type, right? We have integer, right? Which has a range, obviously. Like, for example, for memory, you might have a range from like 1 kilobyte all the way to like the whole memory. Even you can set that options bigger than the memory. You can set this configuration, but the system would fail when you deploy it under this configuration, obviously. But you can technically set any integer value as you want. You have also other options that are continuous, right? Some systems have options that are technically continuous. So we have a good variety of variables involved of different type. Typically, the range of values coming from the documentation. So, for example, range of value related to software options typically is determined by the developer. Hopefully, the hardware coming from the microarchitecture specification, right? And middleware is the same way. You can find the range in the documentation. If not, typically people would rely on, guess or considering a specific range for optimization. For optimization, you can also consider a subset of those range for your task, honestly. But the best benefit is that the causal graphs support all of these types, from categorical to continuous to to integer, etc.
Perfect. Thank you very much for your answer.
I would like to also mention one thing very important. Why, for example, causal AI approach? What are the other benefits that we get? The most fundamental consequential benefit that we get out of this method is that, because otherwise, what would have been the option? I didn't have time to go through all existing work. For example, there are many different work relying on ML for performance tasks. Like
Pooyan, we are a little bit over time, so I want to let you continue your last pitch, but let's hear a quick 30-second elevator pitch. Why Causal AI over other ML, and then we'll wrap up and let our captive audience go.
Perfect. The pitch is that Causal AI enable generalization for performance tasks across many different environments. Why? Because irrespective, like comparing to ML, where you estimate a conditional probability such as neural network probability of y given x, here you have the ability to intervene and basically estimate the interventional distribution, estimate the underlying data generating process for all environments that you want to incorporate, which otherwise is impossible with like normal regression-based or correlation-based approaches. That's it. Cool. I have several other benefits, but that is the most important one.
Yeah. Really interesting stuff. So thank you so much, Pooyan, for coming on today and teaching us a little bit about Causal AI. Thank you to our audience as always for tuning in and listening, and thanks especially for the lively discussion in the comments. As always, you can go to our website, mlsys.stanford.edu. There you can sign up for our mailing list. We promise not to spam you. I think we send literally 2 emails a week. So you can, subscribe to our mailing list for updates. So like I said at the beginning of this video, we're actually gonna be going on summer break now. So we'll be back in mid-September. And if you're at Stanford, you can sign up for a course. It will be CS 528, the Machine Learning Systems Seminar. So we'll be back in mid-September with another slew of great speakers. Meanwhile, if you're watching on YouTube, subscribe to our channel. Hit the bell icon to get notified when we go live. If you're watching the VOD, leave a comment about your favorite part. But with that, we'll say thank you to the speaker, thank you to the audience, and wave goodbye.
Thank you.